When I was a little boy, I took an interest in Albert Einstein and his physics as well. He could sit at a table, drink tea, and work on his mathematics. And what did he work on? The bending of light, the curving of space-time, Einstein-Rosen bridges. Wow. Albert Einstein wrote 350 science papers over 50 years. In 1905, he wrote his theory of special relativity. A decade later, he published general relativity. General relativity explains what gravity does, but not what gravity is. Einstein spent the last 4 decades of his life trying to unify gravity with electromagnetism. He couldn't get the pieces to fit together. Yet he knew somehow they should be related. Einstein was also the godfather of quantum physics. He tried so many clever approaches until one day he realized what was needed hadn't been discovered yet. Wow. He told his colleagues, "Look a little deeper for hidden variables." They laughed at him, yet in 1964, less than a decade after his death, they discovered quarks, charged particles inside of protons and neutrons. I've studied Einstein's work for 5 decades, piecing together the puzzle of how to unify gravity and electromagnetism. I have a theory of how they are related. Let me begin by saying Einstein was right. The quarks are the key. The 3 charged quarks are bouncing around inside protons and neutrons at a length scale of 1 femtometer. The quarks produce a tangential electric field, and I've set out the equation for you, where a is the acceleration back and forth within distance d. By the small field approximation from general relativity, we of course get Newton's law of gravitation. We see that the force of gravity is proportional to the tangential electric field of each of the 2 particles. By dimensional analysis, we find then that the force that is tangential is d squared over k times the dot product of et1 dot et2. Einstein left us good breadcrumbs to follow. General relativity is a tensor theory. You can see, for instance, how straightforward it is to arrive at Newton's theory of gravity in the small field approximation, g m over r squared. And in this presentation, I will assume there are 2 similar protons that are feeling a gravitational attraction to each other. So now, let us set the g mu nu to be equal to the force that's coming around about as the quarks jiggle back and forth. If you expand it out, you have the dot product of 2 cross products. The fact that this is proportional to 1 over c to the 4th is encouraging, because that is what you expect in Einstein's theory of general relativity. In terms of what's in the absolute value sign, when you go through a logical series of steps and you use the fine structure constant as the charge to charge interaction, which seems reasonable. When you equate the two expressions, you find that G is going to be equal to 6.81 times 10 to the minus 11 newtons meter squared over kilogram squared. This is within 2% of the standard value. If Einstein had lived a decade longer, he would have found this out for himself. Things get even more interesting if you study this not at the level of protons, but of quarks. Then we find that the value for G depends on the admixture of the quark-quark interactions, resulting in different interaction strengths. For instance, proton on proton would be 25 over 18. Neutron on neutron would be 16 over 18, and proton on neutron would be 15 over 18. On the surface, this might seem strange. For materials that have heavy nuclei, our measured value of G would be the standard value. There's no surprise here. But what about light nuclei? There's a profound oversight when it comes to hydrogen and hydrogen. We have never really measured G between two hydrogen clouds whose masses were measured by inertial means and not gravity. The Ottfoss experiment is meaningless here for obvious reasons. Two clouds made of hydrogen would result in a force that is 25 over 18 squared larger than expected. That's a difference of about 90%. Astrophysicists can't seem to fully understand the dynamics of cosmological structure, inventing dark energy and dark matter, almost in desperation. 10% normal matter and 90% dark. I wonder if the only place in the universe where dark energy and dark matter truly exists is between the ears of astrophysicists. There once was an ether, until in 1905 Einstein did away with it. If Einstein were around today, I wonder what he would think of the new ether, dark matter and dark energy. He would probably say, look a bit deeper, or maybe, as the godfather of quantum physics, he would have sat down, thought a bit, then written the paper, Is Gravity Caused by the Tangential Electric Field from Some Atomic Particles? He would have noticed the proton to neutron magnetic dipole moment are nearly in the same ratio as interaction strengths in the theory. 2.79 over 1.91 is approximately 25 over 16. Is this a mere coincidence? In 1916, Einstein wrote about gravity waves. He thought they would never be discovered. A century later, they were. If gravity is a residual quantum effect caused by the tangential electric field from quarks trapped within the confines of protons and neutrons, then this is also the quantum theory of gravity we have been looking for.